Hi, I'm Paul. We are doing Leetcode must-know interview questions. Today's challenge is count complete tree nodes. This is rated as easy. The challenge is given the root of a complete binary tree, we'll talk about what that is, return the number of the nodes in the tree. According to Wikipedia, every level, except possibly the last, is completely filled in a complete binary tree, and all nodes in the last level are as far left as possible. It can have between 1 and 2 to the h nodes inclusive at the last level h. I'm not sure what that means. Design an algorithm that runs in less than O(n) time complexity. Okay, well, what that means is we got to come up with something better than just counting all the nodes. So there must be something about the property of complete binary trees that we can use to get a count of the nodes without actually traversing every node. Okay, any more constraints here? Number of nodes in the tree is somewhere between 0 and 4 zeros, 50,000. Node value, okay. So it's possible that the initial root will be null. Let's do this. Well, let's see. Let's calculate the depth of the right subtree and the left subtree. Okay. So if we start with the left subtree, what is the depth of that tree? It's 2. Okay. If we start over here, what is the depth of the right subtree? That is also 2. If those are equal, that means that the left subtree is what's called a perfect binary tree. Okay, it has all the nodes that it could have. If we have a perfect binary tree, we can compute the number of nodes just by taking 2 to the power of the depth of the subtree, which is 2. So 2 squared is 4. That counts all the nodes in the subtree plus the root. 4 nodes. And then we do a count nodes on the left subtree. Really, this is a recursive call to it's a recursive call to the method that we called on the root. We need to count the nodes because we really don't know over here whether this is a perfect binary tree. And in fact, it isn't. So count nodes on the right subtree will give us 2 for a total of 6. Okay. The other possibility is we take the depths of the subtrees and they're not equal. How would that happen? Well, let's say this 6th node wasn't there. It's still a complete binary tree. And now we can be sure that the right subtree is a perfect binary tree. And we can get a count. The depth of it would be 1. So 2 to the first power is 2. and that gives us the count of the right subtree and the root. We then do a count nodes on the left subtree. We have to do a count nodes because we've already postulated that the 6 is not there, but we don't know if the 5 is there. We know the depth is 2, but we don't know if the 5 is there. So we have to do a count nodes on it. And when we do a count nodes on it, we'll get 3. That'll come back up. And again, we are imagining that the 6 is not there. 3 plus 2 is 5. Okay. This doesn't make a huge difference in a small tree like this, but it can make a big difference in a large binary tree because you can visit an exponentially fewer number of nodes if all you do is follow left nodes down and get the depth of the tree. All right, so let's try an implementation. Count nodes. Let's say if root equals null, which is a possibility even for the root node, we're going to return 0. Because the constraints do allow for an empty tree. All right. Let's say now we'll compute the depth of the left subtree. So left depth equals compute depth, and we'll give it root dot left. Okay. Copy that. All right. Compute the right depth. Oh no. Oh, I copied that. All right, then the right depth. All right, so as we said, if those are equal, if left depth equals right depth, then the left subtree is a perfect binary tree. So we can account for all the nodes in the left subtree plus the root by raising 2 to the power of the depth of the left subtree. It's 2 to the second power. And we will return, let's do this, left depth. Doing a shift like this is a way of raising raising 2 to some power. So 1 in binary, if we shift it left 2 places, it becomes 2, then it becomes 4. So that is 4 if left depth is 2. And we will add, I'm going to scoot this over so I have enough room. We're going to add count nodes and give it root dot left. Okay. This is actually very similar to what we're going to do in the other case. Here we'll say if they're not equal. if they're not equal, that tells us that the right subtree is a perfect binary tree. So return 1, and we'll shift by the right depth, which is 2 to the power of the right depth, plus count node. I messed this up. This should be count right. That should be count left. That's it. We don't have a function called compute depth, but that's okay. You can create one. That can be a private method. Private, it's going to return an int. Compute depth, tree node, well, compute depth, I don't really want to call it, I don't really want to call it, well, maybe I do. I don't really want to call it root, because we're not even computing the depth from the root. We're computing the depth from the root of the subtrees. So let's just call it node. Okay, start out with depth equals 0. Let's say for, is there another way to do this? We can do a while loop, while, yeah, I think a while loop actually makes more sense to me. Let's do this. While node is not equal to null, we'll add 1 to the depth, and we will say node equals node dot left. Okay, once we've done that, return the depth. I think that's it. Compute the depth of the trees. We have a computation that should work if the depths are equal, and we have a computation that should work if the depths are not equal. So let's run it and find out. Accepted. Okay. And submit. Oh, beat everybody. Okay, that's good. That's good. Because sometimes you get this, and it's like everybody is clustered in one one bar. But actually, we got 10% of solutions took longer. That may be, they may be doing additional traversals. So that is the solution for count complete tree nodes. Thanks for watching. Feel free to subscribe, like, comment, and see you next time.